title of my talk today is development of high capacity anodes for rechargeable alkali metal batteries using nanostructured alloying materials. I guess that should be alkali metal ion batteries. So I specifically didn't put in lithium ion batteries because we're expanding beyond lithium ion now. So I have a couple of slides at the end on sodium ion and potassium ion battery development that we're doing. But I will say the main focus will be on lithium ion battery development. Okay, so just to give you an overview of what I'll be talking about. So first, I just give a brief background to lithium-ion battery technology. So what's the conventional technology at the moment, and why we're looking to alloying materials, specifically at the anode. I'm going to talk about the importance of nanostructuring alloying materials, and why it's important that you have those nano dimensions for a stable capacity retention. Going to look at something that's a very important component of a lithium-ion battery, which is the solid electrolyte interface layer, and how you stabilize that. And then lastly, how you go about increasing the mass loading of alloying materials for lithium-ion batteries, which is key if you want to commercialize the technology. Okay, so that's a very high level. I'll talk about each step along the way in more detail as I get through it. Okay, so I suppose the talk itself, I'll be going through a lot of background, maybe when we started into lithium-ion battery research, which was way back, published the first paper in 2014, I think. So I'll give an overview of where we started, where we are now, and kind of where we're going with these alloying materials. But to just go to a very fundamental level, I'd first like to talk about the current state of the art in lithium-ion batteries. So lithium-ion batteries are the dominant rechargeable battery technology on the market, and for good reason, is that they have the highest energy density and the highest gravimetric energy density and the highest volumetric energy density, and that's related to lithium's position on the periodic table. So it's the atomic number of 3, so it means it's a very light element, and has a small volume. Also has a very low reduction potential versus a standard hydrogen electrode, which means if you couple it with a cathode material that has a high working potential, well, then you maximize the voltage of your battery, and therefore you maximize the energy density. So you know, lithium-ion batteries are ubiquitous now at the moment. You know, any mobile phone that you have, laptops, any mobile electronics, basically that have a battery, generally will be a lithium-ion battery. Likewise, EVs all have lithium-ion batteries, because again, related to their superior energy density. The operating principle of them is given here in this schematic. So I'm only going to focus on the anode today, because that's where the alloying materials are used, basically, or are applicable. But basically, if you're not an electrochemist, sorry, it's a bit of background noise there. So the operating principle of a battery is basically you have an anode and a cathode, and that's separated by a polymer separator that's soaked in electrolyte, generally carbonate based. At the cathode, conventional materials are layered oxide materials, basically, so something like lithium cobalt oxide, although there's a move away from cobalt now towards nickel and manganese. You can have polyanion type compounds as well at the cathode, something like lithium iron phosphate. At the anode, graphite is conventionally used, so graphite typically will be the majority of lithium-ion batteries on the market today will have graphite anodes. Graphite is a really good anode material because of its layered structure. So graphite is just basically layers of carbon, so carbon sheets, so graphene sheets. And that layered structure is very conducive to long cycle life for lithium-ion batteries, because basically when you charge the battery, what happens is lithium migrates from the cathode across the separator and into the anode, and it intercalates between those layers, and that's not disruptive to the structure of the graphite. It means you can do that reversibly over thousands of cycles with little capacity fade, at least from the anode, or at least related to the structure of the anode. So that works really well. But one issue is graphite tends to, or does have a relatively low specific capacity. So it has a capacity of 372 milliamp hours per gram. The reason it has a relatively low capacity compared to alloying materials is due to the anode half reaction here, which you can see is this middle reaction here. So for every 6 carbons, only 1 lithium ion can be accommodated. Okay, so that's not a very good ratio. So if you move, or if you want to increase the energy density of a lithium-ion battery just by swapping out the anode material, well then alloying materials like silicon, germanium, and tin, so group 4 materials or group 14 materials, they actually can accommodate much more lithium. Okay, so if you look at the alloying reaction here, so if we take silicon to be the example, silicon will react with lithium ions plus electrons to form a lithium silicon alloy, and each silicon atom can accommodate up to 3.75 lithium ions at room temperature. So that's a considerable amount more than what carbon can. So if you remember carbon, 6 carbons to 1 lithium. Here you have 1 lithium, 3.75 lithiums to 1 silicon. So that results in the gravimetric capacity of silicon being an order of magnitude higher than what it is for carbon. So you might ask, well, then why don't you just swap the anode material for silicon? And of course, it's not as straightforward as that, is because along with this alloying reaction here, you get a very large volume expansion. So if you use a microscaled electrode or a film of silicon, basically what happens is it just pulverizes. So the large volume expansion, it can be upwards of 300%, just causes the material to pulverize. If it pulverizes, it loses contact with the current collector, and what you'll see after very few cycles, you'll see the capacity begin to just fall off a cliff. Okay, so there has to be, you have to mitigate that somehow. So that's one of the major challenges with the incorporation of an alloying material as an anode for lithium-ion battery. So it's that large volume expansion that leads to loss of contact with the current collector. There are other challenges, and the second one is an unstable solid electrolyte interface layer. I'll talk about what that means in more detail later in the talk. But basically the SEI layer is because of the potentials that lithium-ion batteries operate at, the electrolyte is unstable. So what you get in the first cycle or the first initial cycles is you get decomposition of the electrolyte at the surface of the graphite anode, and this happens with silicon as well. So that's this actually is beneficial in a graphite anode because it passivates the surface of the anode, but it's not beneficial in a silicon electrode because it's unstable. So what you get is you get continuous decomposition of the electrolyte with every cycle. So that's something that does need to be overcome if you want to cycle silicon or germanium for thousands of cycles. Another challenge related to these alloying materials is that it's difficult to get commercially relevant mass loadings. Okay, so you want to be upwards of 1 milligram per centimeter squared for silicon, certainly, and probably even beyond that, so above 1.6 or 1.7 milligrams per centimeter squared if possible. So that is a challenge, getting that amount of material onto a current collector and have it perform stably. Okay, so if we look at the first challenge then, so overcoming the loss of the contact with the current collector related to the volume expansion. So like I said, if you use micro-sized or micron-sized particles or films, basically all you get is pulverization. So there was the seminal work on the use of nanostructured silicon was done by a professor E. Chui in Stanford back in 2007. He published this in Nature Nanotechnology. So he put forward the use of silicon nanowires instead of films or particles. So nanowires are very good material as an anode because basically you can grow them directly from the substrate, you can grow them directly from the current collector, which means you don't need binders or conductive additives, which are inactive materials that would be used for graphite electrodes, for example. So they're inactive, so it means they don't add to the capacity. So they reduce the overall specific capacity of your anode. You don't need those for nanowire type anodes. So, like I said, the professor Yi Chui in Stanford pioneered this technique, so to use nanowires grown directly from current collectors as the anode material. What that does is, because every nanowire is directly contacted to the current collector, you get good electrical and efficient electron transport from the current collector. The nano dimensions then mitigate against pulverization. So nanowires won't pulverize. So the stresses within the material, because it's nanostructured, are much less. So they don't crack and lose contact with the current collector. Now they do change their morphology, which I'll get to later, but they don't lose contact with the current collector, which is very, very important. So that kind of led us to our very first publication in this area, which, like I said, was back in 2014. And it's useful to talk. I know that that's a long time ago now, but it's useful to talk about it because this gives a good sense of how these nanowire type materials behave and kind of how they change their morphology as you cycle them. So we started looking at germanium nanowires first. So Kevin in his lab has developed the solvent vapor growth system for nanowire growth. So basically, the solvent vapor growth system is you have a long neck flask that you place into a furnace, a high temperature furnace. Within that flask, you have a high boiling point solvent, and also within that flask, you place your current collector with your seed material attached. So the current collector in this case was stainless steel. The seed material was tin, and those tin seeds, when you inject in germanium precursor, will seed nanowire growth. If you reflux it at 430 degrees for 10 minutes, you get nice dense nanowire growth on the surface of the current collector. So we decided to look at germanium first, I suppose, because germanium has not only does it have a high capacity, it's not as high as silicon, I will say, it's about a third that of silicon, but it has much higher conductivity and a higher lithium diffusivity. So we decided to look at germanium first. When we did, well, sorry, this is what the SEM of the nanowires after growth, so this is pristine material. And you can see you do get dense nanowire growth across the substrate. And there's a high mag image there where you can clearly see the tin seed at the end. So what we did then is we took that material and we used it as the working electrode in a Swagelok type cell is what we use. So Swagelok type cell is a very basic test cell that we can assemble quite easily in the lab. So what we had was, on one side, it's a 2 electrode setup. On one side, we had the nanowires grown directly from the current collector. On one side, separator soaked in a carbonate-based electrolyte, and then the other was the counter electrode was lithium metal. So when we charged and discharged these, we found that they had an excellent capacity retention. So we were able to get well over 1,000 cycles with excellent or minimal capacity fade, I would say. So there was a capacity fade initially, but which stabilized after more or less, you can see a slope change here after about 100 cycles. And beyond that then was very stable. So we were obviously very happy with this. From 300 cycles on, you can see the electrode retained about 99.1% of its capacity. So which we were, as I said, we were very, very happy with. So we wanted to look into why they performed so well. So we did some material analysis before and after cycling to kind of investigate what does the material look like afterwards. So the prevailing wisdom in the field at the time was that nanowires perform well because they maintain their morphology. So they don't pulverize and they maintain the nanowire morphology. So what we were expecting to see after 1,000 cycles was that we would take apart the cell, wash the material, have a look at it on the SEM or the TEM, and we would still see our nanowires, albeit maybe slightly deformed. And that's not what we saw. So what we saw was this porous network of ligaments, basically, of the active material of germanium. So we investigated that further, and we did kind of staged charging, staged cycling of these. So we looked at the material after 1, 10, 20 cycles, 300, 100 and 300. And what we saw then was the progressive deforming of the morphology. So after 1 cycle, you still had nanowires. After 10, you could see the structure, the surface, had become much rougher. After 20, it was much more difficult to even make out the individual nanowires. And then after 100 and 300, you can see the nanowire morphology is gone, and it's been replaced by this porous interconnected network of active material. Importantly, between 100 and 300 cycles, you don't see any more deformation. So what's formed after 100 cycles looks almost identical to what you have after 300 cycles, which is very good. And it's the reason why our material has such good capacity retention, is because once this structure has formed, actually now it doesn't deform any further. So once you get down to ligament diameter of about 5 nanometers, it doesn't deform any further. So if you look at a high mag image of that on the TEM, you can see very obvious there now that the nanowire morphology is gone. And as you zoom in, you can see this ligament structure has formed. And zoom in even further, you can see that roughly, approximately 5 nanometer diameter consistently for all the ligaments, which says to us, or which told us that this is actually the stable morphology that you need. So it's this 5 nanometers is the stable morphology. It's not the nanowire initially, it's this structure is the stable structure. Because you'll see this, even if you took the material after 1,000 cycles, you would still see this dimension as well. So it doesn't deform any further. We looked at this process, the evolution of it in a little bit more detail then on TEM as well. What we saw was after 1 cycle, if you look at a nanowire, you can see these pores started to form. So basically what's happening is, you alloy the material and then you discharge it, excuse me, so you de-alloy it, but that leaves behind a vacancy where the lithium has been. Those vacancies aggregate and form pores, and basically there's an energetic driving force for that because it reduces the overall surface area. As the pores begin to aggregate, so as you continue to cycle, the pores begin to aggregate, so you can see the pores get larger and the surface of the nanowires get rougher. Eventually, after 20 cycles now, if you look at a single nanowire, you can see those ligaments beginning to form. So that's just the nanowire is becoming more diffuse. The pores are aggregating, and now what's left behind is these ligament type structures. So that's after 20 cycles. Okay, so we put forward the theory then of what is causing this deformation, and like I said, it's this pore formation coupled with something known as electrochemically assisted welding. So what happens is not only are you getting pore formation and that forms the ligaments, but actually the ligaments, if they're in contact with each other, can weld to each other as well. So that's important because it gives you this interconnected network. So the welding occurs because if you have 2 ligaments in contact with one another, both of them can simultaneously be lithiated. But what you'll get is you can get a lithium bridge bonding between the 2 ligaments. When that lithium, is discharged or delithiates, that lithium is removed, and so there's a kinetic driving force then for silicon-silicon or germanium-germanium bond formation at the interface of the 2 ligaments. So you get welding and pore formation, and both are critical to form that very stable porous structure. Okay, so the ultimate goal then was that was all with germanium. And germanium, while it worked very well, it is unfortunately very expensive. So the goal was to move to silicon. So the initial step we took in that was to look at germanium and silicon on a single electrode. So germanium offers the benefits of the very long cycle life and excellent rate capability, and silicon has a very high capacity and is also inexpensive. So we combined both on a single electrode. One of the issues we had, we wanted to try and grow germanium and silicon nanowires individually on the same electrode, same current collector, but it's difficult because Anything that will seed germanium growth will also seed silicon growth. So we couldn't just grow them, pattern on different seeds and grow them individually. So because you would just, if you tried to grow germanium only, all the seeds would be used up. So what we did then was, rather than grow them silicon and germanium from the current collector individually, we grew heterostructures. So we grew the germanium nanowires first, and then we patterned those with tin seeds. So just so we attached tin nanoparticles basically using a thiol ligand. So ethane dithiol. That attached the tin nanoparticles, and then we were able to grow silicon nanowires from the germanium stems. So we had this branch structure. So this is look at that kind of process on the SEM, excuse me. So you can see you start with your bare nanowire, soak it in the EDT solution, immerse it in the tin nanoparticles, and then grow the silicon nanowires in the solvent vapor growth system then separately. So you get this nice branched structure, and importantly, all the branches are well contacted to the stem. Okay. When we cycled those, we got very stable capacity over 100 cycles for all three different materials. So we looked at three different ratios, I should say. So 2:1, 3:1, and 4:1 germanium to silicon. And what we saw was the higher the germanium content, the lower the capacity, but the better the rate capability. So the reason for that is, as I've said earlier, germanium has much higher conductivity than silicon, and also a better lithium rate of lithium diffusion within it. So we were able to tailor then, basically, by changing the ratios of germanium to silicon. You can tailor either for high capacity. So if you want high capacity material, you increase the amount of silicon that's in there, or you can tailor it for high rate capability. So if you want high rate capability, you increase the amount of germanium in there. And that's important for, it gives you a material now that you can tune. Okay, so graphite you can't really tune. So graphite has its properties, and those properties are set. But with a kind of heterostructure like this, you can tune the performance of it. So for example, if you want something that a battery that has a very high capacity, but maybe you're not too worried about the power density that's achievable from it, something like a mobile phone. Okay, you don't need to discharge a mobile phone very quickly. Well, then you want something, you want the high silicon content there, because that will give you the high capacity. If you want something that has high power capability, maybe like a power tool, well then maybe you want to move towards more germanium. For all cases, we saw that the germanium silicon heterostructure behaved better than silicon on its own. Okay, so, and again, I guess that's what we expected. Okay, so that was the initial studies we had on these materials. One thing, because as I've alluded to on the last slide, we ultimately wanted to get to 100% silicon, okay, because silicon is cheap and germanium is very expensive. So, and also as I've shown you, unfortunately, silicon did not behave, or didn't have the same capacity retention that germanium had. So we knew we had, so while silicon will form that porous, interconnected, stable structure, it still doesn't retain the same capacity that germanium does. So we wanted to tackle that, and we knew the reason for it was the SEI layer, so the solid electrolyte interface layer. So like I said in the introduction, this is a very important component of a lithium-ion battery. Let's check the time here. Okay, so basically what happens is when you charge a anode or a lithium-ion battery at the anode, you'll get decomposition of the electrolyte. Okay, so it's just unstable at those potentials. For graphite, this is not a problem because the graphite has only about a 10% volume expansion when it's fully charged. So what happens is you get decomposition of the electrolyte, and it forms this passivating surface, and that SEI layer is quite stable in a graphite anode. That's not the case for silicon. Okay, so for silicon, because you get the large volume expansion, you do get SEI formation, but it's not stable. So every time, because the volume is expanding and contracting with every cycle, the SEI layer forms and then cracks, and forms and cracks, and forms and cracks. So what that does is it's very detrimental to the performance because you're getting continuous electrolyte decomposition, which is thickening the SEI layer, and that's basically increasing the impedance in the cell. So it does impact the cell's long-term performance. So what we noted was that for germanium, the SEI layer was much more stable than it was for silicon. So we wanted to try stabilize that SEI layer for silicon in hopes that we could mimic the capacity retention that germanium has. So what we did was we looked at a series of electrolyte additives that stabilized that SEI layer. So typically the standard electrolyte for lithium-ion batteries is carbonate based, so you can use DEC or DMC, so diethyl carbonate or dimethyl carbonate, coupled with ethylene carbonate, so they're the solvents. The salt then is a 1 molar LiPF6 salt, and we added 3 weight % of each of these additives separately. So vinylene carbonate, fluoroethylene carbonate, vinyl ethylene carbonate, and LiBOB, so lithium bisoxylattoborate. All of these had been used previously with graphite, and some had been used with silicon previously. So we knew they had stabilizing effects on the SEI layer. So when we coupled them with silicon nanowires now, so these are 100% silicon nanowire electrodes, we saw that there was a huge variation in the performance. So the VC outperformed all the rest by a margin. The FEC and the LiBOB performed similarly in terms of capacity retention, but the LiBOB, you can see the data was not the smoothest of data, I should say, and VEC the same. The reason for that was, well, it's related to the SEI layer, but those are temperature effects basically. So as the temperature in the lab fluctuated, as the temperature went down in the lab, you get a reduction in capacity for those electrolytes, or when you use those electrolytes, and when the temperature goes back to room temperature, or you know, so nighttime temperature is low, you get a low capacity. Daytime temperature is higher, you get a higher capacity. So the VEC and the LiBOB were much more affected by temperature than the rest, and basically we didn't show this, but previous or other groups had shown that the reason for that is the SEI layer has an Arrhenius dependence basically. So the lithium diffusivity through the SEI layer has an Arrhenius dependence, and that's more affected by those two electrolyte additives. Okay, when we looked at the actual material then, after cycling in each of these electrolytes, we noted that for VC, so the best performing one, we did get this morphology transformation again. And actually for the 3 best performing one, we did get that morphology transformation, and you can see that ligament type structure forming again. For VEC, we did get it as well, but we also found these kind of amorphous kind of areas as well that did not have that ligament type structure. When we used no additive at all, the ligament structure did not form. Okay, so, and that clearly showed why the no additive doesn't retain much capacity at all. It's because you're not forming a stable morphology, or you're not evolving into a stable morphology. So if you looked at SEM images of these, you can see then clearly that the no additive, a lot of the material has actually, when you wash it, you lose a lot of the material. So it's not well contacted to the current collector, whereas with VC it is, and actually for the 3 best performing ones in terms of capacity retention it is. So even after washing, you can see the material is still very well adhered to the current collector, whereas the no additive one, you can see a lot of bare patches there. The reason for that is because, again, the no additive one is not forming that stable morphology. It's forming this kind of amorphous mass, which is not well contacted to the current collector. We did some XPS to analyze the chemical composition of that those SEI layers. What we found was, so I'll direct your attention to the C1s spectrum, that for the 2 VC and FEC electrolytes, there was a significant concentration of poly-VC in the SEI layer. And this is something we expected because it had been shown for graphite previously and for other silicon type electrodes. But basically, what poly-VC does is it's a polymer, obviously, but it provides flexibility to the SEI layer. So if that's in there in large enough concentrations, you get a more flexible SEI layer. So when the silicon expands, then it's less prone to cracking. Sorry, the SEI layer is less prone to cracking. If the SEI layer is less prone to cracking, you don't get this continuous deformation and reformation of the SEI layer. So you don't get this continuous decomposition of the electrolyte. Or at least you do get it, but to much lesser extent than for a no additive type material. So that the presence of that poly VC was very, very important. For VC and FEC, we found it to be in there in around 6% concentration by weight in the SEI layer. For LiBOB, it's not obvious here, but we did find it as well. It was in there in about 1% concentration, so that explained why that did have a high capacity retention. LiBOB, the capacity retention can also be explained by some other element or other compounds that we found in the SEI layer. So boron semicarbonates, for example, that are less prone to dissolution. So not only with the SEI layer do you get cracking, but as you discharge to 1.5 volts, for example, in a half cell, you can get dissolution of the SEI layer. And LiBOB forms those boron semicarbonates are less prone to dissolution. So that explained why this one had a high capacity retention, even though the amount of poly VC was much less than in the VC and the FEC. We looked at this XPS here is of the SEI layer. We also we did XPS of the actual active material. So we washed off the SEI layer and just did XPS of the silicon that was left behind. This provided a very interesting result in that when we looked at the no additive material, we actually couldn't even detect elemental silicon. So now XPS is obviously it's a surface technique, so it probes around 10 nanometers in, but we could not find elemental silicon. So what that told us was that the SEI layer is so unstable that it keeps cracking and recracking. So not only does it keep the SEI layer keep reforming, but when it does so, it actually consumes the silicon. So it's consuming the active material. So it's not only that the solvent molecules are decomposing, they're consuming silicon at the same time. And they form these lithium silicates, so these LiX-SiOY type compounds. Once they form, that's irreversible, so you won't get the elemental silicon back. So this really explains why the no additive material doesn't form that ligament type structure, doesn't form that stable morphology, because basically the silicon is being consumed continuously. So you get that consistent capacity degradation when you don't use an additive. Okay, for all the other ones with the additives, fair enough, we did find those silicates as well, but we were able to detect elemental silicon. So below the surface, 10 nanometer, or at least within 10 nanometers, we were able to detect elemental silicon. So it gave us a good indication why, as I said, the no additive doesn't form that stable ligament structure, whereas the additives do. We looked at ionic liquid electrolytes as well. We did this in collaboration with a group in Rome, so Gianni Epitecci, and a group so he's from ANIA, and a group in KIT, so Professor Stefano Passerini. We looked at ionic liquid electrolytes. Won't spend too much time on this, but we did find that we could get a boost in performance with ionic liquids, but we had to have those carbonates in there. So we had to have either EC or VC, and VC was the best again. Interesting point on this study was the majority of studies previously using ionic liquids for silicon had used the TFSI anion. We used a combination of the FSI and TFSI anion, and that gave us, it was the best performing silicon nanowire electrode in an ionic liquid at the time of publication. Now, maybe that has changed now, but at least at the time of publication it was. The reason for that was the FSI actually gives the electrolyte a lower viscosity and hence a higher ionic conductivity. And that's the main reason. There are other reasons as well. So modeling, not in our paper, but in other papers, shows that Li+, so lithium ions, have a weaker electrostatic interaction with the FSI anion than they do with the TFSI anion. Therefore, it favors desolvation if they're solvated by FSI, So that lowers the energetic barrier to charge transfer. So that was, we had a couple of interesting papers on that. Okay, so that's the SEI layer, and the last major challenge then is the low mass loading of nanowires. So to be, if we look at a commercial graphite electrode, typically they have a charge storage capacity of about 4 milliamp hours per centimeter squared, and that would correspond to about a mass loading of 11 milligrams per centimeter squared of the graphite. If you want to just match that with silicon, and if you assume a capacity of silicon, that your silicon is going to deliver a capacity of 2,500 milliamp hours per gram, you would need a mass loading of silicon nanowires of about 1.6 milligrams per centimeter squared. Whereas if you look in the literature, the typical mass loading of directly grown nanowires is much lower than that. So it's about 0.2 to 0.4 milligrams per centimeter squared. So that's clearly an issue if you want to commercialize silicon. So we just published a paper in Advanced Materials. So Sumer was the first author on this, tackling this problem basically. So looking at, can we increase the mass loading by using different types of current collectors, and also can we increase the flexibility, which is important if you want a flexible battery. So basically what was done here was we took a stainless steel fiber cloth using the same nanowire growth technique, so using the solvent vapor growth system and using tin seeds. So Sumer, he evaporated on the tin seeds, and then in the solvent vapor growth system grew the nanowires. You can see this is an SEM of the pristine fiber cloth, and this is a SEM of the seeds after evaporation. We wanted to, because mass loading was one of the key parameters we were looking at here, we wanted to look at a range of mass loadings to see how it affected the performance. So by varying how much tin you deposited on, whether you deposited on single side or both sides of the cloth, and by varying reaction time, we were able to vary the mass loadings to between about 1/4 of a milligram per centimeter squared up to 1.3. So we couldn't reach the 1.6, which we tried to reach the 1.6 milligrams per centimeter squared, but this was the max we could get. So we had 4 different data points at least. If you looked at the cloth after growth, you can see from the low mass loading to the high mass loading. Clearly for all of them, you get a dense growth of nanowires on the surface, but for the higher mass loading ones, the fibers of the cloth are no longer visible, okay, which is good, okay, so, and is what you would expect, I guess, if you've denser growth in there. But that's what you want, because you can see that the spaces in between the fibers are difficult to make out, and you can see that nanowires from individual fibers are all intertwined with one another. So that's important, because what you want is that material to be well adhered to the current collector. And so if it's all intertwined with one another, then it will, because if you have a planar current collector and you increase the mass loading to this level, the nanowires can actually behave somewhat like a film and delaminate and peel off. So we didn't want that to happen with this cloth, obviously. So the structure of the cloth prevents that, because the nanowires basically intertwine with one another. And we were able to show that quite simply using sonication. So if you took a stainless steel foil versus the stainless steel cloth and you sonicated it for up to an hour, the foil, you can see the nanowires, the solution becomes progressively darker, and that's related to the nanowires just coming off the foil. Whereas if you do it with the cloth, you get no, or very little at least, nanowires coming off. When these were tested in the battery, so they gave a very good performance. So we could get up to 500 milliamp, or sorry, up to over 1,000 milliamp hours per gram for over 500 cycles. Importantly, I suppose, while the very high mass loading one didn't retain the same capacity that the lower mass loading one did, it still performed very well and was well over twice the capacity that graphite, or that's achievable with graphite. What was interesting was actually they both tracked the same, or more or less the same capacity, up to about 200 or 250 cycles, and it was only beyond that then that the higher mass loading one begun to decay a little bit faster. We did post-mortem analysis of these, and we saw that the interconnected structure did form. I'm probably looking at time here. I'll skip over some of these a little bit, but what was encouraging was, I suppose, that the morphology of the nanowires wasn't at fault here. The morphology of the active material wasn't the problem here. So what we think is it was actually the SEI layer thickening caused the higher mass loading one to degrade a little bit more quickly than the lower mass loading one. And evidence of that was shift in the differential capacity plot peaks to lower potentials. Okay, so flexible batteries was another, or moving towards flexible batteries is another. It's if you look at the tech industry, so Samsung and Apple and all the rest want to move towards flexible phones, and they're already there somewhat. But if you want a truly flexible phone, you need a flexible battery. So using this stainless steel fiber cloth is moving towards that, or is a way to get there. And Sumer did this very nice video, I have to say, showing how robust that current collector is, even with twisting and deforming it. You can see no material delaminates or comes off the surface, which is, you know, exactly what you'd want. And even after the twisting and deforming, he put that into a cell then, and you saw you got very good capacity retention as well. So it had no effect on the capacity retention of the silicon, which was great. Okay, so that's kind of where we are. Where we're going now, I guess, is we're still doing a lot of research in lithium-ion battery and advanced lithium-ion, but we're also expanding beyond that too. So we're looking to more sustainable technologies as well. So the sustainability of lithium-ion batteries is questionable. So there are a number of concerns around it. So one being cobalt is an essential element in the cathode, or at least in the majority of cathodes for lithium-ion batteries. Cobalt is mined in the Congo, so Democratic Republic of Congo, and there's some serious human rights issues there related to mining. So a lot of child labor and, you know, not so nice things like that. So there's a lot of concerns about cobalt and cobalt mining. Likewise, lithium mining is unsustainable as well. So the reserves are limited. They're concentrated in Australia and South America. And while the reserves are not an issue now, but the EV manufacturing is ramping up. So if you look at Ireland's targets, Ireland want to have 1 million EVs on the road by 2030. So that's a lot of lithium that's going to be required. And that's just Ireland. So if you look globally, the demand for lithium is going to increase. So because the reserves are limited, that may have an impact on price. More importantly, the mining is actually, it's not a very sustainable process. So if you look at lithium mining in South America, lithium is mined from salt lakes, basically. So the lithium is in there, it's dissolved up in these salt lakes. So to get the lithium, they evaporate off these brines. So they evaporate the water off the brines. To get 1 ton of lithium carbonate, you have to evaporate off 500,000 liters of water. And these are already in areas, a lot of the time, that water is actually a precious resource. So they're, you know, in quite dry and arid areas. So that's not a sustainable process at all. So there is a move to look towards more sustainable batteries. Edmund mentioned the Trident project. So one of the goals of the Trident project is to develop a sodium-ion battery. So sodium-ion battery is much more sustainable now, because sodium obviously is ubiquitous. You know, sodium in the form of sodium chloride we find everywhere. Okay, so you'll have it in the cupboard at home, I'm sure. So sodium-ion batteries eliminate the requirement for lithium and cobalt. The materials are much more sustainable. They're also less costly. So sodium salt, or sodium carbonate, is less than 10 times the price per kg of lithium carbonate. And the supply chains can be located entirely in Europe. So if you're looking at a hard carbon anode, or the elements in the cathode, which are much more ubiquitous, like sulfur, phosphorus, iron, and so on, it's long-term sodium-ion battery that there's no real risk to the supply chains, which is another advantageous property of it. Another good thing is that you can actually leverage the knowledge, the decades of research that's gone into lithium-ion. You can leverage that in sodium-ion because the chemistries are similar. They're not exactly the same, obviously, but they're very similar. Because of the cost reduction, you do have the potential to reduce the cost of energy storage to less than 5 cents per kilowatt per cycle, which is a key target of the EU. Okay, so what we wanted to do is look, or what we are doing now is, and this is not part of the Trident project, this is a separate SEAI project, I should say, that Stephen O'Sullivan is doing this research. So he's looking at alloying materials rather than hard carbon as the anode. So what Stephen is doing is he's taking the copper current collector, he's growing inactive nanowires, so these copper silicide nanowires that are inactive materials. So basically they're acting as a current collector, but a high surface area current collector. So this is what the nanowires look like. So they're conductive. He then coats them with tin and antimony. So he evaporates on a bilayer, 20 nanometers of tin and 20 nanometers of antimony. He does that because basically they buffer each other. They charge, or they sodiate or ally with sodium at different potentials. So while there is a volume expansion, each material tends to buffer the other during their respective volume expansion. So you can get an increased capacity retention by doing so. So Stephen has, because we're looking at relatively novel materials here, Stephen has developed his own concentration of electrolyte and developed his own electrolyte. So he uses FEC additive with DME, and that gives the benefit of both the carbonate-based chemistry and lime-based chemistry as well. And he's gotten reasonably good performance with these. So he's not long into this project, but he's gotten up to 250 cycles with relatively stable capacity retention. And actually, he has over 1,000 cycles with on a bilayer on a planar electrode as well. So that's very promising. This work as well is to move even beyond sodium ion to another more sustainable battery technology, is to look at potassium ion batteries. So for the same reason that sodium ion battery is more sustainable and low cost, potassium ion batteries have the same or similar properties as well. If you couple that with the low reduction potential of the potassium ion versus standard hydrogen electrodes, so it's about minus 2.93 volts. Whereas if you look at lithium, it's minus 3.04. So they're very similar. So and that's what you want for an anode material. So you want it to have a low reduction potential. So potassium ion batteries are advantageous in that respect. So Sumer is taking a very similar approach to what Stephen was taking, except Sumer is using these copper meshes, and he's growing the copper silicide nanowires on those copper meshes, and then he's evaporating on the antimony onto that. So you can see this is what the copper mesh looks like. And if you zoom in, he gets very good and consistent growth of the copper silicide nanowires. Again, these are they're not active materials, they're acting as a current collector almost, and a high surface area current collector. Sumer has excellent capacity retention with his material as well. So we're very close to 1,000 cycles with these. So 1,000 being a very good milestone, or a really nice milestone. So we're hoping that there's no electricity blackouts or anything that stops this one, but it should reach 1,000 cycles, and we're hoping to get publish this and get reasonably high impact publication from it, because it vastly outperforms anything, to the best of our knowledge, any antimony based paper for potassium ion batteries on the market today, or published today, I should say. Okay, so that is it. So first of all, to conclude, I suppose I'd like to acknowledge all the co-authors on all those papers that I just talked about. In particular, maybe call out Kevin and Hugh for long time collaboration with both of you. So thanks for that, and all the other co-authors and funding agencies. Thanks for the support. Okay, so that's it.
Thanks very much, Hugh. I'm just looking to see if there are some questions in the chat. 1 second, and while I'm doing that, I have two particular questions, Hugh, or Tadhg, sorry. In terms of the sodium and potassium, how do they compare in terms of the lithium-ion battery? In terms of where, like, you've got great performance now, and you want that if you get to 1,000 cycles, you'd hope you'd be able to publish that. But how does that compare then with the lithium?
Yeah, so I suppose one thing, if you're to compare the technologies, one thing I should say is, yeah, lithium ion will always be the dominant rechargeable battery technology in terms of energy density, always. And that's just related to the atomic size, basically, and the energy density you can get from it. So the goal of the sodium ion and potassium ion research is not to compete with lithium ion in terms of energy density, but it's to compete with it in terms of sustainability and costs. So certainly you can have a much more sustainable battery and a much lower cost battery, albeit it might not have the same energy density as lithium ion. But so I suppose the applications then will be different. So for lithium ion, the applications are electric vehicles, mobile electronics, things that you have to carry around with you that you need to be small.
Yeah.
But if you're looking at an application like stationary storage of, renewable energy, for example, it's a battery that does not need to be moved around. That's where sodium ion and potassium ion will have their niche.
And how they compare? Like, is there an order of magnitude difference, or is it 50%, or what's the?
No, it's so if we look at sodium ion batteries, so if you look at there actually are sodium ion batteries commercialized at the moment, and energy densities, I think off the top of my head, there's one produced by AMTE Power in the UK. It's about 160 watt hours per kg.
Okay.
If you look at lithium ion, you can get about 260 watt hours per kg. So it's not a million miles away from it.
Yeah. One of the things I was curious though as well, when you're looking at I think it was sodium, you need to also use a tin, I think, to see the at least in the initial process. And you didn't have a challenge then, because tin is also in relatively short supply, or it's an element where it's not readily abundant or readily available like silicon would be, or sodium.
Yeah, and I would definitely agree with that. Yeah, I would definitely agree with. So the long term, I suppose, there's going to be different anode materials in sodium ion, and some are probably more sustainable than others. The hard carbon one, for example, which we're looking at in the Trident project, is a really sustainable one. We're using, or we're taking some of Morris Collins's lignin-derived hard carbon and using those. So that's very sustainable. But if we want to move to tin, we can get higher capacity. So there is a trade-off, I would say, between elemental abundance and the energy density that you can get.
Yeah. So you're not reliant on tin solely then, unless you want the performance. Yeah.
Exactly. If you want the higher energy density, so the energy density or the capacity of tin is about 3 times that of the carbon. You see, so there are definitely trade-offs.
I had one last question, Tadhg. Just going way back to one of the slides you had there, where you were talking about the nanowires and you're getting delithiation, and you kind of had a cartoon of almost the pores and the actual walls of the wires, and then they kind of welded and cross-linked. And what I don't understand about that is when you're removing the lithium, you're creating a vacancy, but that indicates then that it's not just intercalation like you would have it with the lithium-ion battery, where you've a graphite anode. Is that correct?
Yeah, no, that's absolutely correct. Yeah, so it's not intercalation, definitely not. No, it's an alloying that occurs. So because
but then is it harder then, because you have to you start to form these germanium or silicon bonds to compensate for the vacancy? Do you then have an activation energy barrier to actually recharge that electrode, because you have to break those bonds again?
Not really, because those bonds are present anyway within what's left behind. So for example, if you have 2 nanowires side by side, after you delithiate, you still have, a porous nanowire, for example, but you still have the silicon bonds. So if you have 2 nanowires side by side that are connected, the driving force there is actually, if they are connected to one another, the driving force there is to reduce the overall surface area in contact with the electrolyte. So that's what that does. That's why that silicon-silicon bond forms. So it's a surface energy. It's reduced the surface energy more than anything else. But you still, whether the welding formed or not, you would still have silicon-silicon bonds within the material anyway. You know, so it doesn't inhibit lithiation afterwards.
Yeah. Okay. Thanks very much, Tadhg. I don't see any questions in the chat unless somebody is. If not,
yeah, sorry, Edmund, there are
Marina.
sorry, Edmund, there are a couple of questions there in the chat.
Yeah. Okay.
Oh, how are you?
Hi, Kevin, how are you?
Good, no, good, yeah.
Yeah. Actually, I was.
So, Tadhg, do you think that the tin seeds on the tip of the silicon nanowires have any effect on the properties of the material? In terms of conductivity, as an example.
They certainly do have they play a role as well. We didn't look at conductivity, but the tin actually is an active material too. So the tin is will actually reversibly alloy with lithium as well. So it's not it's not in there just to seed. It actually is active as well. So it actually increases the capacity of your material as well. Yeah, we didn't look at conductivity, but definitely that was something we were able to highlight, is that we could see additional plateaus and peaks in differential capacity plots that were related to the reversible alloying of the tin as well.
Okay. And Hugh had a question there, Tadhg. First of all, great talk, and I'd agree. And the question Hugh has is, do you think the stainless steel cloth anodes could be used for bipolar cell design to maximize the energy density?
I would say yes. So the bipolar design is where you want, you need active material on both sides. So these stainless steel cloths are, they seem very amenable or optimal for that. It's not something we've looked at, Hugh. But I think, certainly looking at some of the European calls coming down the line, maybe these bipolar type designs are something that maybe the battery industry is moving towards. So I think it's certainly something we should and maybe will look at.
Okay. Thanks very much, Tadhg. And I don't see any other questions. So could I just say well done, and it'd be great to see you get to 1,000 cycles in that last test you're running, and hopefully you'll be able to get that published fairly soon. How long does it take in terms of what sort of time frame is that?
That's a good question, actually. Funny story, I had a conversation with Sumer about that only last week or the week before, and he knows exactly how long that one is running, because he put it on around the same time his son was born. So it's about 6 or 7 months now, I think, at this stage. So while his son obviously is his most important thing in his life, this test is his work baby. So
okay. Well, hopefully go over 1,000.
Yeah, hopefully.
Right. Thanks very much, Tadhg, and thanks very much to everybody for attending. Okay, that's it for today. Thank you very much. Bye bye.
Thanks, Evan.